Good afternoon, and thank you for joining us here on Think Tech Hawaii. I'm Ethan Allen, filling in for Jay Fidel on Research in Manoa every Monday afternoon here at 1 o'clock. And today on Research in Manoa, we have Anupam Misra. Welcome, Anupam. Very nice to have you. He is a physicist, geologist, geophysicist.
Physicist.
Background here, got his doctorate in physics from the University of Hawaii here, and is still here studying geophysics and planetology in a way, and doing all sorts of cool stuff that we're going to get into. And I was saying to you before the show began, it seems to me that your work encapsulates and embodies a core aspect of science that's often sort of goes without saying. People don't think about it, but one of the things that science does is extend our senses. It allows us to see things that we can't see, or hear things that we can't hear, or feel things that we could not otherwise feel. And a lot of your work, it seems to me, really pushes those frontiers in a lot of interesting ways. Is that a fair encapsulation of some of that?
Yeah, kind of. So we try to do the remote sensing and chemical detection,
Mm-hmm.
so things you wouldn't be able to tell by just your own common senses.
Right.
Then you could use these technologies to tell the difference between different chemicals or find stuff that you're looking for.
Yeah.
And so we're mostly in remote sensing for chemical detections.
Okay, so that's a big field with a lot of interesting aspects to it, and you actually, I guess, cover a fair range of those, from sort of geological prospecting almost down to sort of anti-terrorism approaches by looking for explosives, right?
Yeah. We have two kind of projects funded. Most of the funding comes from NASA for looking for minerals or Mars or biological stuff on, say, Mars or other planets. So we developing instruments for those goals. And the other type of funding is coming from the ONR, Naval Research. They're looking for identifying chemicals which may be explosive or non-explosive or just regular chemicals, and from a far distance.
Excellent. So tell us, one of the things you use is this remote Raman systems, and I gather this is an active detection where you shoot something out basically and then get some information back.
Yes. So our approach is we develop active technologies where we are not be shooting a laser and the laser interacts with the material, and then it gives you some photons that which are due to the interaction you get different types of photons, and then you analyze those and you can tell what kind of material you were interacting with. So in active laser technology there are three major ones. One is the Raman, and other one is called LIBS, which is laser-induced breakdown spectroscopy, and third one is fluorescence.
Okay.
And so we kindly focusing on these three technologies here.
Okay, and it's because, of course, laser is very coherent radiation, and so it, in theory, it bounces off of things. When it bounces off of things, presumably it's losing that coherence, and different things are happening depending upon what it was interacting with, right?
Kind of.
Okay.
So basically we use laser as a source of energy. Most of the time, like, people are using laser, like, the policeman giving you speeding ticket. He's just looking at your speed of vehicle, and so he's looking at a relay signal.
Sure.
Where it's the same kind of photons that comes back.
Sure.
So whatever you're shooting it's coming back. What we are looking is not for the laser. We are looking for what kind of different photons are coming back.
Okay.
So that gives you information about what kind of chemical it was there.
So are these photons knocked off of the substance, or?
It came from the material.
Ah,
yeah.
okay. So it's not the laser coming back.
It's not the laser
stuff
that
that's been
had that-
excited by the laser, basically. It's been
Yeah.
jazzed up, and now it's shooting off, basically.
Yeah.
Ah, I see. Okay. So it is a fundamental difference that I understand.
It's not LiDAR. LiDAR is
Right.
pretty common. So
Right.
we are doing something different phenomena there.
Right. And so, of course, if you're doing this for NASA, you said you have to be building instruments that are extremely lightweight, because every ounce you send up is, of course, a huge amount of propellant to get them up there. Extremely rugged, able to operate in very extreme environments, and extraordinarily reliable, right?
Yeah, kind of. So the NASA projects comes into different phases. So they have different programs where you develop an instrument, then the next step is to miniaturize and space qualify, and the third final step is that it launches to the other missions. So we have been developing small instruments. They have to be small so they can be, so we are competing with other groups, so our goals are to make our instruments smaller than the other groups. We are part of Mars 2020 mission to send instruments, so some of our design is actually now is part of the SuperCam instrument, and they'll be on Mars. Launch is 2020.
Excellent, excellent. And for those Mars projects, what specifically are you looking for there? What are your instruments being set to find?
There is already a laser-based instrument called ChemCam. It's developed by Los Alamos National Lab, and that's a remote LIBS instrument. LIBS is basically you have the laser, so it stands for laser-induced breakdown spectroscopy. So you take the laser and you focus on a target, and so what it does, it takes the material and takes it apart. It makes atoms out of it. And then when these atoms, they go from excited state to ground state, they emit light. So you can tell what atoms were there in the molecule. And so that's called LIBS, and the ChemCam is already working on Mars. So the next instrument is actually going to be Raman plus LIBS plus Fluorescence. And so we are helping with the Raman part. They already have the LIBS technology working pretty good. So Raman, so in the LIBS, you can only tell what kind of atoms are there.
Right.
But then you don't know what molecule it is. So for example, if you have a lot of organics have the same carbon, nitrogen, oxygen, just 4 elements. So it's difficult to tell is it TNT versus sugar, or so the Raman comes in. It's very unique technology where all the molecules have very unique Raman spectra. So if you have, say, and military can use it too, like if you have a grain of TNT in your finger, it's 100% guarantee if you do Raman on it that it's a TNT and it's not your powder or your makeup or something.
Okay, so this is intriguing me. So the LIBS actually essentially vaporizes some material
Yes.
and actually probably turns it more or less into at least a gas, if not a plasma, really?
Yeah, yes. Yeah.
And so, yeah, it's got a whole bunch of very excited individual atoms with highly excited electrons, and then they're gradually cooling slightly and emitting photons.
Yeah, that's the process.
So then the Raman doesn't quite tear things apart that much, right?
No, Raman is kind of non-destructive.
Okay.
So if you think about Raman, it's actually looking for the vibration between 2 atoms. So in a molecule, there are many atoms, and
Right.
they're always vibrating.
Sure.
So simple way to think is that if you have only 1 atom, so it only moves, it can rotate, but it doesn't vibrate. So in order for you to have a vibration, you at least need 2 atoms. So simplest will be like hydrogen gas or nitrogen gas. So then you have 2 atoms vibrating. But this vibration frequency is very specific. It depends on the mass, it depends on the chemical bond. And so each molecule gives you a very unique spectra. And so if you know the Raman spectra of a chemical, then if you measure an unknown chemical, you can easily match it up.
So it's like looking at a piano string and being able to tell what note it was because of just how it's vibrating, right?
Just how it's vibrating.
Each of the 88 strings is vibrating a little bit differently.
Yeah, it's exactly like
in a much more complex way, I'm sure.
It's kind of same, actually.
Okay, excellent. That's great. And then you mentioned one other thing. You mentioned the fluorescence use.
Fluorescence use it's not very specific, but there are some advantages that the signals are stronger. So you could use it for certain applications. If you want to detect like biological material on Mars, then we have an instrument that can tell you that looks like this probably be more biological than other minerals. So you can do a very wide area search in a very fast time, because the signals are almost 1,000,000 times stronger than the Raman signals.
Okay.
So you can run as a video speed, the instruments.
But it's not quite as specific.
It doesn't specify, but it tells you the shape. So if it looks like, a dead insect, then you see a dead insect there. So sometimes the shapes helps.
Right.
You can see if it's a leaf or a flower or an insect or
Sure,
something.
that can give you a great deal of clue. So this is really actually that triad of techniques, and really gives you a lot of different kinds of information. The atomic breakdown of it, the sort of molecular structure of it, and some information about how it
How
really
the shapes
is
are
shaped.
and how the distributions
Right.
are.
Excellent, excellent.
So no one technique actually can tell you everything you need. So
Mm-hmm.
there are certain strength to certain techniques because they give different types of information.
Sure, sure. Just as in medicine, they may do X-rays or MRIs or
Yeah.
CAT scans to get slightly different images of different things within you.
Yeah.
Right, same kind of idea. Okay, excellent. So, what have you been working on here on Earth with this?
On Earth, basically, our goals are to detect chemicals in the daytime from a very far distance. And the detection time is less than a second. So if you have something 200, 400 meters away, and you want to know if it's dangerous or what kind of chemical, if somebody's drying some chemicals on the roof, what are they, if somebody's making drugs, or you can identify those from a far distance in 1 second.
Ah, okay.
So there are a lot of applications
So
there.
you put this instrumentation up in a drone, and
You can put it on the drone. So eventually, goal is to make smaller instrument that can go on the drone, and then you can fly
over neighborhoods,
or you
and-
can
yeah.
scan. Yeah.
If you think somebody's up to something no
Yeah,
good.
and
you
it's
can-
also useful for hazardous management where you have a chemical spill. You don't know what kind of chemical got spilled. You want to identify before you send in people for rescue.
Right, you don't know if it's invisible, you may not know how far it's
Yeah.
gone, and this
Yeah.
could detect where it is, where it isn't. Okay. This seems like, again, a lot of good
A lot of
applications.
applications.
Yeah, excellent. So how did you get started in all this field?
Actually, came from a physics background, so my PhD was in high-TC superconductor.
Okay.
But most time when you are working, your funding in certain area actually dries out. So you're never working in the same area. So you have to keep moving as different fields are getting funded.
Sure.
So yeah, now I'm in this because there's some funding here.
It is intriguing how many scientists do.
You have to keep moving around, so you
around.
never go back to the things you really want to do because there's no funding there.
I guess some people sometimes circle around, as it were, because
And come back.
after a few rounds, the technologies are so new now that you can look at it in a new and better
Different,
way,
yeah,
right?
yeah.
Yeah, my old advisor keeps studying fish vision, but he's spun around several times, and is using much more sophisticated techniques to look at the genes that control fish vision now, rather than just the eyeballs of the fish. So it can be quite the journey, I see. Anyhow, so this is great. We've got a good sense now about what you do. We're going to get into this in some more depth here in our next segment. But right now, we're going to take a short break. I'm with Anupam Misra from the Hawaii Institute of Geophysics and Planetology, and we're talking about all of his exciting work in Raman, Libs, fluorescence imagery. We'll be right back.
You're watching Think Tech Hawaii, offering lifelong learning from passionate hosts and fascinating guests ready to explore and explain Hawaii's place in the 21st century. Great content for Hawaii from Think Tech.
Aloha, my name is Richard Emery, and I host Condo Insider. We talk about issues facing the condo association throughout Hawaii and talk about solutions. When you think about it, about 1/3 of our population lives in some form of common interest real estate. We broadcast every Thursday at 3 p.m. Please tune in and thank you. Aloha.
Aloha, I'm Kaui Lucas, host of Hawaii is My Mainland, here on Think Tech Hawaii every Friday at 3 p.m. We address issues of importance for those of us who live here on the most isolated landmass on the planet. Please come join me Fridays at 3 p.m. Mahalo.
And you're back here on Think Tech Hawaii, research in Manoa every Monday afternoon at 1 o'clock. I'm sitting in, Ethan Allen, I'm filling in for Jay Fidel, who is out of town right now. Anupam Misra is my guest here from HIGP, Hawaii Institute of Geophysics and Planetology, part of SOEST at the university. And we're talking about his work in remote Raman, libs, and fluorescence capabilities. It's all about chemical detection, about finding chemicals at a distance usually. And we've got some visuals to help us really get our hands around some of this stuff. So take us through what you're showing here.
So here are some of the systems that we developed. So there's some smaller systems that are developed for NASA funding, and there are some bigger systems. They are developed from the ONR funding, military funding. And so I'll show you some of the data from each of the system and talk about what they can do.
Okay.
And so here is one of the bigger system. Bigger is kind of medium size. It's not huge or something. It fits on a trolley. Basically, what we are showing here that we can detect a chemical which is 120 meters away.
So there's a little
so-
sample of chemical down at the end of that long hallway?
Yeah, there's the green spot is where the laser is shooting,
Okay.
and there's a chemical. And by looking at the Raman spectra, you can tell exactly what kind of chemical it is.
Wow.
And these measurements are actually done in 100 nanoseconds.
Wow.
So it's less than 1 second. So it's pretty fast.
Just a quick
Yeah.
snap and it's done.
And so there the graph shows that even very similar chemicals, like, there's only KClO3 and KClO4, they're pretty much similar, but Raman spectra are very different because the arrangement of the atoms in the molecules are different. And so our systems are actually very reliable. They are, work in the daytime. You can do in the daytime measurements.
So
That's the important part. Like, you want to do things in the daytime where the sun is there.
Okay, so why is daytime versus nighttime so important?
The Raman spectroscopy has been there for, almost 90 years. It was discovered in 1928. And so in the past, it was just basically a technique for looking at chemicals under the microscope in the dark, because the signals are so weak. So if you have room light that actually saturates your detector, then the signals coming from the material.
See, the other light is basically causing a lot of background noise.
Yeah, and so your signals are pretty much weaker compared to the.
But you've now developed
So now
this.
we have developed a system which actually can work in the daytime, and you generate enough Raman photons that they are above the background of the daylight, and then you detect them, and so the sun doesn't bother you. So it opens up more applications.
Sure, okay. And going on to your next thing for your chemical waste sites and all?
So it has a lot of applications. You can detect things which you don't want to touch. You're doing a remote sensing. So here is example of, say, concentrated sulfuric acid. And it's like useful for, say, airport security. You have a bottle which you don't know it's water, you have something, or somebody left something. So here you can detect something, what it is, and you can tell what's inside. It's 100 nanosecond. You can scan the whole thing if you need to. So we see application in terrorism or waste management, where you're burning things, but you don't want to be burning something which can give you toxic waste and kill a lot of people.
Okay, so if they have these on the airplanes, pretty soon we can carry our water bottles through security.
Yeah,
and
they actually, it's easy, so at least you shouldn't be able to throw your water away.
Right.
Yeah.
Yes, it's very annoying in the TSA lines.
Yeah.
You have to dump your water bottle.
And you carrying milk, and then they don't want you to carry milk and all.
That's right, okay. Good, all right.
So the third slide, if you want to see, so here we're showing that there are different types of containers, but since we're using a laser, it has to penetrate a little bit. So we can detect things which are very dark in color. So even 1% transmission is enough for us to tell what's inside a bottle. So we were able to detect things which with your normal eyes you wouldn't be able to tell what's inside a plastic bag or things. But with the system we have, we can tell what's hidden inside the plastic bags and all.
Wow, so yeah, even when they're wrapped in bubble wrap or plastics.
You couldn't tell them.
Now, if they were wrapped in something truly opaque like foil,
then you cannot.
Right.
So then the system doesn't,
Right.
so every system has some advantage
Right.
and some disadvantage.
Right.
So the advantages are like, now people are not making things in metal because they got to go through the metal boxes. So
Right.
the things are now hidden in plastics.
Right.
So then you have to figure out how you're going to detect plastics and different types of plastics.
yeah, but there must be some interesting technological challenges because of all the different kinds of plastics that are used for wrapping now. I mean,
Yeah, so certain things works pretty good. There's always then research and development. So you also don't want to tell what things works and what don't work because then it's easy
Right.
to defend.
Sure, sure. Don't wanna give
Defeat
away
the
secrets,
purpose.
right?
Yeah. So
Exactly, but that's great, that's great, excellent, excellent. And moving on to your next thing here.
So here is just giving example of, say, ammonium nitrate is interesting. It's used for a lot of homemade explosive.
Okay.
So it's important chemical to detect. You normally don't use ammonium nitrate for your daily purpose. If somebody's carrying it, it's a suspicious item.
Right.
So here we are showing that we can detect through bottles without opening it. And then you can also tell different types of plastic bottles from the signal. So when the laser goes through, it actually measures everything which comes in the way.
Sure,
So it measures the air, it measures the plastic, it measures the chemical inside, and so on.
Right, so it's giving actually a lot of information,
Lot of
but
information.
teasing it out rather nicely for you, so you know,
Yeah.
because you've studied enough of this, you know what's the bottle material versus what's in the
Well,
bottle.
yeah.
Yeah, excellent, super. Wow, this has really gotten very sophisticated then.
Be pretty good in the remote Raman.
And you must have computer algorithms that read these things.
Yeah, you
and-
can. Yeah, these are very standard database. So if you get a peak at 1043, it's pretty much nitrate.
Okay.
And then by looking at the other peaks, you can tell it's potassium nitrate or ammonium nitrate or some other nitrate.
Excellent, excellent. And moving on.
So here's example that is a bottle of ammonium nitrate hidden in a plastic wrap. And so the bottom, so one side has bottle, other side doesn't have bottle. So if you measure the area which doesn't have chemical, then you see only the plastic signal.
Oh, okay.
And then if you move the laser up, and then you see some extra signal, means something is hidden there. And then you can tell what it is.
Okay, right, because you could easily take
You can just take it
one
out,
signal
yeah.
from the other and just leave the plane.
And the advantage of Raman is just simple addition. Is A plus B plus C and so on.
Oh,
So it doesn't shift in the signal. and all.
okay. No matter what they've wrapped it in,
Yeah.
the signal comes through unabated. Yeah, okay, great, super. And you got another one of your more distant detection systems here, I guess.
So here is our 8-inch system. We are looking, so there are two students. One is the graduate student Tyro. He's just going to finish his PhD. And the other one is undergraduate student Dalton. And basically the systems are easy to operate, when the Dalton can operate it.
Okay.
And it's easy to train. So they are going to, that's the overall size of the system. You have a telescope, you have a laser, you have a computer, you have a scanner that you can target where to point the laser,
Okay.
and so on. So in the next slide, we show how far we have measured so far. And so we are actually trying to measure a chemical, or several chemicals we measure at a distance of 430 meters. And that's the target on the far side of the building where the green spot is.
Wow.
In the next slide, I think we zoom in and it shows where the target is. So that's where the samples are. And these are the detection in 1 second. So you can see they are very good signal to noise ratio. You have high confidence in what you detected. And this is the daytime in the sun in like 2 o'clock in the afternoon. So samples are in the sun.
Right, so and these are 4 different chemicals. That
Four
you might see.
different chemicals, and there are 2 measurements for each chemical, showing that the system doesn't deviate from us. It has a lot of reproducibility there.
And again, some of these chemicals you would have no real business carrying with you.
Oh yeah, you shouldn't be carrying these. potassium nitrate,
Right.
ammonium nitrate. Unless you're in the farming business, you need to carry some nitrates.
Right.
But
Fertilizer or whatever, right.
For fertilizers.
Right. Huh, okay, it's incredible to see how you're able to do this with small samples at great distance in quick time.
Yeah. So you can do very far. Our goal is to go to kilometer range. So far we have tested 430 meters, but we want to go even more, longer distance.
Wow, that could be amazing to really work that distance. And you can work through even very bad conditions, I gather.
Yeah, so Raman systems, so because it's a spontaneous signal, so you fire the laser and the Raman signal comes instantaneously. So if you're using a 10 nanosecond laser pulse, your Raman signals are also lasting for 10 nanoseconds. So if it's raining or if it's a dust storm, it doesn't bother the detection so much because everything is kind of frozen in that nanosecond frame.
Right.
So we took our system to the Mojave Desert, and there was a dust storm during 2007, and so nobody else went in, but we were up. They say, gotta be up at 7 o'clock. So we were up, saying, there's a dust storm, nobody's going out. So, we are up, so why don't we just try it? So we were the only people, we went on the truck and tried to test the system in the dust storm. And we could measure things in a dust storm. So we have a video, but probably put it online sometime. But you could measure during the dust storm without any problem. So these measurements are actually through a truck. So the system is on the truck, but since it was a dust storm, we closed the truck. We had 2 windows to protect the system. So it's actually measuring through two glass windows.
Plus a bunch of dust.
Yeah, and then you can measure. These are single pulse measurements.
Again,
And you can measure through bushes, as long as the laser goes through.
Yeah, that's a great advantage of doing that really quick at 10 nanoseconds. You're not, nothing's happening. The dust isn't moving at that point.
No,
The
it's
dust
not
particles are basically still.
Kind of frozen.
Yeah. That's a great advantage of doing it that fast. Yeah. And can you do this stuff like down into the ground or in water?
You can do it in the water. So we have one project from ONR. They want to detect things which are in the ocean, sea mines or debris or what they are for the port security. And so we took the system, and basically if you are going to fire the laser at an angle, it's just going to reflect off. So these system will work if you're looking down, from an aeroplane, so it's better to look normal to the surface of water.
Sure.
And so we don't have a helicopter. So what we do is we put a mirror to make it look like it's going down. So there's a mirror. So we fire the laser to the mirror, and the mirror directs it down to the water.
Okay.
And then we have this plastic bottle which is 2 meters deep in the ocean, and we could tell what chemical it was and what plastic it was, and then it's seawater.
Wow.
Yeah.
Again,
So
it's all the same stuff.
and
that you've
that's
done
single
before.
pulse too, like in 100 nanosecond, you can tell.
Amazing. Well, this is being absolutely fascinating, except for really stunning that the technology has developed to where you have this sort of very sophisticated capacity. And we're going to come back and probably talk about some more of this, maybe where this is all leading. But we do have to take another break right now.
Okay.
I'm Ethan Allen, filling in for Jay Fidel here on Research in Manoa, every Monday at 1 o'clock. Anupam Misra is with me today, and we'll be right back.
Aloha, my name is Carl Campagna. I'm the host of Think Tech Hawaii's Education Movers, Shakers, and Reformers. You can see our show every Wednesday at noon at 12 p.m. on thinktechhawaii.com, as well as visiting YouTube and finding the link for the show there. The show is also aired on OC16. We look forward to seeing you on the show. We have many wonderful guests, including Joan Husted, Corey Rosenlee, where we talk about the very important issues of education for our keiki. We look forward to seeing you there. Mahalo.
Aloha, my name is Justine Espiritu, and I am the co-host of Hawaii Farmers Series. This is my co-host, Matthew Johnson, and we are live with you every Thursday at 4 p.m. at thinktechhawaii.com. And our show focuses on Hawaii's local food community. We feature not only the farmers that are producing our food, but we also feature the supporters and other folks involved in the community that are trying to promote local agriculture.
And we're back here in research in Manila. I'm Ethan Allen here on Think Tech Hawaii, filling in for Jay Fidel. And with me is Anupam Misra, a physicist who does all kinds of fascinating imaging technology, Raman, libs, fluorescence, ways of shooting various forms of radiation basically at objects, getting them to react to it, and then picking up very quickly and very neatly the signals that they shoot back, and being able to tell a great deal about these different materials. And it can be used for sort of basic geological phenomena. It can be used for detecting chemical spills. It can be used for detecting hazardous substances in limited environments. So it seems like it's got a broad range. It's truly, indeed, my other show is Likeable Science, and this is sort of likeable science because you see there's a lot to like about it, you know. So you have this compact Raman plus libs system that you had a slide about, which was a fairly complex image here, but walk us through these if you would, please.
So for NASA projects, they want smaller systems,
Okay.
and they want, if possible, several systems in one system, so its overall size is smaller. So here we're showing our Raman and libs system, which uses just the regular camera lens for instead of a big telescope.
Okay.
And this system can measure Raman spectra, say from 9 meters, or 10 meter. We have tested up to 50 meters, so it can also work at 50-meter distance. And so but NASA is mostly interested in detecting what kind of minerals are on Mars, or if there are water or there are biological stuff. So these are the examples of detecting some of the minerals with the system using Raman in 1 second from 9-meter distance. And here we're showing that we don't need big telescopes, so the systems can be smaller.
Yeah, and these relatively small samples of these materials?
These are, at 10-meter distance, you can do, milligram range. Yeah. So
That's amazing.
That's kind of small.
You would think it would be picking up everything around it, and the 10 milligrams would be lost in the substrate. But
No, it's as long as it's, and if they're mixed, then Raman signals are mixed of mineral A plus B and so on.
But again, they can be teased apart then if you sort of
Yeah,
have
you
some
can.
knowledge of it. Yeah.
Yeah.
Excellent. It's just amazing. And it brings me back to my question that I always have here. During our breaks, I've asked a couple times about this. So on the small islands in the Pacific, there is some thought that there may be freshwater reserves buried deep down, thousands of feet down under these islands, under the rocks that underlie the islands. Is there ways that these kinds of systems can be used to answer that question? Because it makes a difference. If it's saltwater, nobody cares. But if it's freshwater, that's a huge resource for them.
So it may be possible, like if you can shine the lasers at the source, and may be possible to excite the thing and tell the difference between water and salt-containing water. And if it's hidden under the rock, then maybe you have to run a fiber probe.
Just a small drill first.
Small drill, and then so you can at least, you need to have the laser actually exciting the material.
That struck me when you were doing your thing on water.
Yeah, so if you can
ideally,
look at the water, you can probably tell.
Right,
People are using Raman for telling what the temperature of water is, what the pH is. From that information, then you can tell if it's fresh or not fresh.
Interesting, yeah. And of course, it probably is helpful to some extent if your probe tip is under the water, so you're not getting that surface problem. But of course,
people are developing fiber-based Raman, fiber probe,
Right.
and that can go anywhere where
Right.
you want to measure.
But then you're getting better images, but you have much more limited area rather than being 1,000 feet up and covering a much broader area, right? Yeah. Always these trade-offs.
Yeah.
That's amazing. So a lot of what you do is actually, in a way, it's a very sophisticated engineering too. It's looking at these problems and saying, what are my constraints? What are my needs here? If I
Yeah,
sacrifice
so-
A to get more B here.
Yeah, so most of the projects are very specific what you want to detect, and so the system designs are just very specific to that kind of goals.
Yeah, excellent.
So it doesn't apply to everything else in
Right.
the world, yeah.
Yeah, excellent. And you've done some more.
So this is example of the libs. So same system, if you focus the laser, then takes the material, takes it apart, put it in the atoms. So it produce lip signals, and lip signals are basically atomic spectra of individual atoms. And so is showing that we can do, and we have to do under the Martian conditions. So we have a Mars chamber where you fill in with CO2 at low pressure, and then you say, okay, our systems are working fine. So just some examples of what, you can, in libs, you can pretty much do all the materials on the periodic table.
Wow.
Yeah.
And every one of them has a unique signature, basically.
That unique part is not there. So the unique part comes only in the Raman.
Okay.
So all the organics will look the same in the libs,
Okay.
because they are all the same atoms.
Just carbon.
But each atom is unique in the
Okay.
libs.
Okay. And some, you might get some information from if there's more carbon, less
Yeah,
nitrogen.
yeah. You
but-
can kind of classify that it has more carbon or more nitrogen.
Right, but
So
yeah.
people are using libs for even quantifying if this is dangerous, or has more nitrogen content than the regular chemicals.
Right, but you can detect basically each individual element. With
You
the
can,
libs,
yeah. So that's the advantage, and it's very sensitive, so you can do ppm levels. So you can, it has an application like, if you're processing core or the soil for the gold mining or uranium mining. So you can tell this soil is rich in gold, and doesn't have that much, so you don't need to process all that material. So it has some application in the industry.
This could be very useful. I gather parts of Serbia, Croatia, where back in the 90s when they were doing a lot of fighting, they were using shells that were coated with highly enriched uranium to make them hard and armor penetrating. And now there's a lot of uranium
Oh yeah, you
scattered all over, basically.
You can easily tell if you have uranium in the soil.
So
yeah,
you could
yeah.
map out areas
Yeah.
that need cleanup versus areas where you don't have to do as much cleanup,
Yeah,
which could
yeah,
be incredibly
that's right.
valuable to help determine where work needs to be done, where people should be staying away from more.
Yeah,
Oh,
yeah.
excellent. Just one more way. This is, wow, I begin to see this. So these are, in this image you were showing here, this libs, this was a mixed sample with all these different kinds of.
No, so we are showing that because it goes in a chamber, and you got to seal the chamber with CO2 and have a Mars atmosphere. So they're just all these different minerals.
Right.
So we just rotate different minerals instead of loading one and unloading one.
Right.
So you just can do all the measurements in the same
I see,
same
okay.
setup.
Huh, cool, excellent. This is just amazing stuff. And let's just see, carrying on through your thing. And then you've got a prototype of a new machine here.
So this new machine is important for NASA. So it's we call it Biofinder, and it's not maybe so important on Earth because everything is biological here. So there's no need to find a plant here on Earth. But on Mars or other planets, it's very important. Like you found something biological, and the task is difficult for the rover because you're looking at collection of minerals, and then most of the instruments are okay. I'm gonna measure there. I'm gonna measure there. So if there is an instrument that can take a video and tell you, okay, that material over there is biological, you study that, and there will be much faster way of searching for life on the other planets. So we have made an instrument called Standoff Biofinder. Standoff means remote, so we don't take samples, we just taking pictures of things, and they can be run at very fast imaging.
So is it based on other technologies detecting, for instance, carbon-based? You want that would be
It's
sort of
basically
first clue, right?
Yeah, so we actually use the fluorescence,
Okay.
but a lot of things give fluorescence and phosphorescence. But we were able to separate out the fluorescence or luminescence from the mineral versus the biofluorescence. And so that makes it interesting because people have been studying fluorescence for a long time.
Sure,
So, but we can, in the daytime, we can separate out a biofluorescence material from the mineral collections.
Wow.
And that's the advantage of
There's a-
doing this.
They fluoresce in different ways.
The biofluorescence is very fast.
Ah.
So you can make the detector which is synchronized with your laser, and so you excite and you measure, and in that time frame the other materials are not giving you signal.
Your chemical stuff is taking a while to build
So
up.
it's, yeah, so
basically.
the minerals takes longer time than the milliseconds, where the biological stuffs are in nanoseconds. So you can separate out these two types of materials.
Very ingenious, very ingenious.
So we call it, biofinder, useful for, at least telling you, okay, you look there.
Sure.
Instead of just randomly going scanning and all. So
Right.
it can save a lot of time.
Yeah, and this is going to be very important in looking at Mars, for instance, because there's a whole huge
Yeah,
issue whether
yeah.
there is life on Mars or was life on Mars, and this will help answer that question. And
Yeah, that's the whole purpose of this. It's not so useful for detecting T-shirt is not useful.
right.
So
And then,
the example of this in the,
Mhm.
I
Right.
think it's slide before.
okay, oops, there we go. Okay.
Yeah, this slide.
Right.
So here we are showing the example that you have collection of minerals and there's some biological stuff we put in, which are harder to see. You have some twigs and some eggshells and some coral, but in the biofinder, all the biological materials, they stand out at the same, just 0.1 second image. That's the image that shows all the materials which are biological in material.
Wow.
And the next image is the fluorescence from the mineral.
Mhm.
So, so this is another application of the technology where you can use it in the water or ocean.
Right.
And so you can say, the plants like coral and ocean plants, they will also fluoresce.
Uh-huh.
But the goals are not to see the fluorescence, but people want to see, or military wants to see if there are sea mines.
Uh-huh.
So the Raman doesn't work actually in detecting metals.
Okay.
So there's no signal from the metals. But you can use this fluorescence or the Raman signal from the water to illuminate an area. And then things which don't have signal, then they stand out. You can tell, oh, there's a razor blade there.
Oh, okay.
So you kind of detecting in a
By the
different way
absence.
by the absence of the signal.
Excellent.
So this is a technology that you can actually tell if there's something man-made object is there than the natural object.
Excellent. So
And-
this could be useful in searching for that downed plane, the flight 3, whatever, from
Yeah.
Air Malaysia that disappeared. If you're,
Well, it's
So-
too deep that one. But these are for example, you can easily detect very small amount of oil leak. So the right side of the image is just 1 drop of crude oil in 2 liter of water, just 50 ppm. So it's like 3 micron thick oil film, which you don't see with your
Right.
eyes. But with our instrument, you can tell, within 0.1 second, or this much oil there. So it can be useful for if there's an oil leak, how much is for the aerial survey. So when the drone technology improves, then it's much easier to just actually scan the ocean, see where the oil is going, or where your other chemicals are going, which they use for, dissociating the oil into different chemicals.
well, this is utterly intriguing. I had not realized that the breadth and depth and sophistication of this technology, and how you've merged interesting technologies together in such a great way to get this power. This is truly impressive. And I very much thank you for coming on here and
No
talking about
problem.
this exciting piece of research. And I look forward to hearing more about it.
Oh, okay.
Thank you.
Nice meeting you.
Bye-bye.
Bye.
We'll be back next week. Bye-bye.